Well, thank you to NARUC and also to GMLC for hosting this important event. I hope that all of our listeners are safe at home and are healthy. It's a strange new time that we're in, isn't it? So my name is Ben Sigrin, and I'm a researcher at the National Renewable Energy Lab. The focus of my research is on two aspects. First, on developing methods for forecasting adoption of distributed energy resources, primarily rooftop solar, but other resources as well. That's one half, that's the mechanical half. And then the other is more on what are the behavioral drivers of technology adoption? Why do people adopt new technologies? How can we represent those better in models? What are the aspects of the technologies that people care about, and so forth. And I also should give credit here to my colleague Andrew Mills at Lawrence Berkeley National Lab. While I'm presenting today, Andrew did develop the majority of the content that you're about to see. So thanks to Andrew, who couldn't be here today. So, when I was first asked to participate in this forum, I immediately said yes. One is I'm very passionate about this topic. I find distributed energy resources really fascinating. Evolution of the power grid. What role do they play in the future trade-off of bulk power resources versus distribution connected resources? And then the second reason was that it's pretty rare that you get to talk to regulators for 45 minutes and no one stops you for asking a question about your content. So I'm very happy to be able to stand here on my soapbox and say my piece. So the goal of this talk is really to give you a kind of introduction to what are current methodologies for forecasting distributed energy resources. Why does it matter? And what influence do they have on the distribution system planning process? So next slide, please. Okay, so again, why should we care about including distributed energy resources in our load forecasting? We've been forecasting load for ages. We've been doing IRPs for ages. Why does this matter? Why now? I think the one thing I'd want to start with is when we're talking about distributed energy resources, not always, but we're typically talking about customer adopted resources. And so there is this exogenous element, this uncertainty about who's going to adopt, when, at what quantity, when does the curve stop becoming linear and look exponential, and so on. So I think the main thing to understand is there's a lot of uncertainty of adoption. And so how those are incorporated into the resource planning is quite critical. But of course, DERs do fundamentally affect the load forecast in several ways. So the first is the adoption or deployment of DERs can affect the types of investments that are optimal to make in this distribution system. As we replace aging infrastructure, we may need to think about how do we plan smarter to accommodate growth in DERs, either adding to load or subtracting to it. Second is these resources are resources. They can't provide every service, but they can certainly be helpful for contributing to meeting peak demand by virtue of reducing the net load that's served from the bulk power side. Third, is related to the first point I made, which is if we anticipate that adoption of DERs may exceed the capacity of the distribution system to accommodate them, then we should also be proactive in forecasting when those needs will occur, and therefore building out infrastructure to meet it as the investment occurs. And then finally, it's helpful to consider this in the broader sense, in the policy sense of evaluating the costs and benefits of various incentives that are underway, either to spur investments in areas that we'd like to see more deployment in, or if we believe that we're overcompensating DERs and therefore want to readjust that level of market compensation. So I should say what this talk is not about. It's not about rate making. I'm sure several people are curious about that. It's not about net metering and how terrible it is. We're not really talking about incentives, and this is not a value of solar study. So it's mostly cut and dry about forecasting methodologies. Thank you. Next slide. So this slide illustrates one of the reasons why we should care about forecasting DERs. And this goes to what is commonly called as the deferral value of DERs. So here you can see on the blue line what the peak load on a distribution feeder might be without any adoption of DER. So over time, it may, as load grows on the feeder, it may at some point exceed its ability to accommodate that much load, and we would have to make an upgrade to the feeder. With PV or other DERs, we might use that resource to defer when that upgrade needs to be made. So the benefit, one way of expressing the benefit is it's the difference in the time value of money between these two times. Instead of making the upgrade now, we can defer it for 5 more years and use those savings in other infrastructure areas. Of course, the peak load may not grow exactly as we show here. It might be the case that with PV, we never exceed the feeder capacity, in which case we defer upgrades altogether in perpetuity. Next slide, please. So yeah, one more forward, please. Thank you. So this slide shows why forecasting accurately matters. So we can intuitively think about 2 outcomes in each direction, either over forecasting adoption of DERs or under forecasting it. So if we over forecast DERs, then that means that we expect more will be adopted than actually occurs. And in which case, if we truly believe that forecast, then we would have under procured generation capacity resources in other areas. So it's bad to over forecast DERs, and likewise it's bad to under forecast them. If we're under forecasting, that means that we overbuilt the system beyond what was strictly needed from a cost minimization point of view. So this study looked at what are the benefits of improved forecast, what is the cost of forecast error, and so cost of forecast error can be quite high. They can range from 70 million for severe under forecasting to 20 million. This is for a prototypical utility that has 10 terawatt hours of sales per year, and assuming a baseline level DPV penetration of around 8.5%. So the value of forecasting is high. It's not infinite and it's not zero, but we should think about how can we improve our forecast and better incorporate those into the planning process. Next slide, please. So finally, Andrew and I and others wrote a study a few years ago trying to survey the landscape of how utilities and others are incorporating distributed solar and DERs into their planning process. So, some of the context for this is that many analysts project distributed solar will continue to grow rapidly across the United States. While it's high in California and Hawaii, we do project its continued growth in other regions. And as I mentioned earlier, forecasting and understanding growth at DPV has implications for many aspects of the utility planning process, and therefore it's appropriate to document and improve our methods for forecasting DPV to ensure ultimately reliable operation of the grid and avoiding unnecessary costs to the ratepayer. So our general approach was to survey 30 recent planning studies, documenting where they were similar, what methods and approaches they took to forecasting DERs, and generally trying to know what is the state of the art, what's sort of the minimum that people are doing. And so our scope of the study is primarily looking at IRPs, but also transmission expansion plans, as well as distribution resource planning. And again, we are focusing on distributed solar in this study, but that's by no means the only DER that influences distribution resource planning. Next slide, please. So we really found 3 key findings in this study. The first is that the field of forecasting DERs is still fairly early, and there are certainly areas of improved coordination that would be valuable. So the main thing that we saw was that forecasting loads with DERs is often done as a top-down exercise, where each aspect is analyzed independently. So first forecasting load, and then the quantity of DERs, and then sort of munging the two together. Second, we found that there are many factors that have been found to affect growth of DERs, and that not all of them are included in the studies. Of these factors, there's one type of methodology that we believe is the most appropriate to use in forecasting DRs, and that's what's called customer adoption models. So these are bottoms-up models that incorporate technical, economic, and diffusion aspects into their forecast. And then finally, forecasts are uncertain. Any forecaster that says that they know what's going to happen is not worth paying attention to. All forecasts have some aspect of uncertainty, and so we do recommend that regulators consider uncertainty, consider the effect the uncertainty would have on the investment decisions, and then also try to gain and gather adoption forecasts from multiple parties to try to understand the range of potential outcomes.
Hey, Ben, we have a poll, I think.
Yes.
Yep. It reads, approximately how much residential distributed solar has been adopted in the United States through 2019? The poll is open, and the four options are 10.2 gigawatts, 15.8, sorry for the typo there, gigawatts, 20.3 gigawatts, 35.1 gigawatts. And we'll give you a moment to think about that. All right, we are approximately at 50%, so we'll close the poll and we'll share the results.
All right. Okay. So most people think it's either 15 or 20, and the correct answer is 15.8, approximately 15.8 gigawatts of distributed solar in the residential sector has been adopted in the United States. Of course, there's more if we include commercial sector adoption, and then of course much more in the utility scale. So thanks. It's a little bit more than some people were thinking, and a little bit less than others. All right, so if we can proceed to slide 7, please. Okay, so regarding the study that I was referring to before the poll, so one of the first exercises we took was to gather what are the near and long-term forecasts of penetration rate of DPV that different utilities have used in their resource plans. And so you can see here that it ranges quite a bit. Hawaii at the far upper end of near 30% penetration rate, but many utilities are well below 2%. One of the things I think that is important to note is there's a wide range of forecast outcomes, both made by utilities or by planners. These are the light and dark blue, but also these don't always align very well with those that are made by third parties. And in particular, most of the third-party forecasts were higher than the utility themselves forecasted. And so it suggests that it's possible, though not always true, that utilities may be under forecasting distributed solar adoption in their territories. Next slide, please. Next, we looked at types of methods that planners have used, and I'll get into detail on what these represent. But basically, we see at least 4 types of methodologies: stipulated forecast, historical trends, program-based, and adoption models. And so you can see that these do result, again, in a wide range of outcomes. Next slide, please. When we documented the deployment drivers, one aspect is fairly clear in the literature, which is that most distributed solar adoption seems to be correlated with the economics of adopting distributed solar itself. So I think from the consumer's perspective, from the ratepayer's perspective, the primary motivation for adopting distributed solar is saving on retail electricity expenses. That's a pretty clear signal that I and others have seen in the literature. So from that, you can make the conclusion that modeling the future economics, payback period, net present value of distributed solar is important. That would include things like understanding future costs and performance improvements, how incentives affect the bottom line to the consumer, emergence of new business models, things like third-party ownership, which is also popularly called leasing, changes to retail electricity prices, both their absolute amount and the structure of the rate itself, and then, of course, other rate design aspects like availability of net metering. There are many other deployment drivers. Policy is probably the second most important, compliance with renewable portfolio standards, or in some cases, projecting carbon tax regulations, and then others, macro factors, and then customer preferences. So next slide, please. So next we look at how these different drivers of adoption are actually incorporated or not into the various methodologies. So I mentioned that there were 4 methods that we see in literature, in practice right now. So first, the stipulated forecast. This is an extremely basic method, and it's essentially an engineering judgment, if you will, about assuming some endpoint for a DPV deployment. It's really not a very sophisticated method. It's not a data-driven method. Next, historical trend, which is another way of saying a time series forecast. So we extrapolate future deployment from historical data. I don't think that's a terrible method, but I don't think it will do well for a forecast more than a few years out. It's perfectly fine to make a near-term forecast based on historical trends, but the real question is, how does the system change and evolve over time, which a time series forecast can't quite do. The third approach is program-based, and this is sort of a pragmatic understanding that policy and other incentive programs are one of the key drivers of adoption. So, for example, if you have a renewable portfolio standard, you might say, well, we don't know exactly how the utility or the other entity will reach its program target, reach its renewable portfolio standard target, but we'll assume that it does by whatever the statutory requirement is, and we just assume that that policies exist to go from point A to point B. So you can see that both historic trend and program-based approach do use at least 2 explanatory factors, using recent installation rates and incentive program targets. But finally, our fourth approach, which again we do believe is the best in class right now, is customer adoption modeling. And so this is a bottoms-up methodology that incorporates many, though not all, of the explanatory factors. It includes recent installation rates. It includes upper bounds on what is technically possible and what is economic for solar in a given year. And it also does include consumer behavior into the adoption forecast. So we'll be spending the majority of our time on customer adoption modeling, what it means and how to do it. Next slide, please. So some planners use customer adoption models, though by no means all, but they basically follow a very similar sequence of steps. So first, the planner attempts to understand what is the technical potential of this resource, rooftop solar in this case. What are the total number of buildings or roofs? What is their average area, and so forth. From there, we develop an estimate of economics of solar on different roofs. What's their payback period? What is the cost? What is the retail bill savings, and so forth. And then we relate that payback period to the second chart. You can see that the longer the payback, longer paybacks are worse. It takes a lot more years to recoup your investment. Leads to a smaller ultimate market share. But whatever that market share is, then the third and final step is diffusing into the ultimate or terminal market share. So this posits that diffusion occurs via an S-shaped pattern of adoption that is ultimately saturating into what we think is the carrying capacity of the system, if you will. Next slide, please. So when we talk about technical potential, as I mentioned, this is typically based on customer counts and rooftops. So this is a fairly common step that utilities use, but the way that they estimate technical potential can vary in its approach and sophistication. So many are basing it based on number of customer counts and average floor space, but there are some really fascinating methods. For example, using LiDAR data, which is a type of aerial imagery, to actually image the roofs. And this can improve the technical potential estimate by understanding how roofs are differently shaded, their tilts, their azimuths. Tilts and azimuths are important because they both affect the generation profile of the rooftop solar. And they can also have more sophisticated exclusion parameters, for example, to exclude roofs that are too small, those that are too shaded, that are too steeply tilted, and so forth. I think that it is possible to, it's certainly possible to overestimate technical potential. So some of the research that my team has done has indicated that there are many other factors that can affect the technical availability of a roof, things like the roof condition, its age, the building's age, whether the building is in compliant with current electrical code. If you're not compliant with electrical code, then you can't interconnect it through the proper means, and also building ownership. So it's So I think that these are different steps that planners can take, but we should also be cognizant of it's not strictly the number of buildings or the total roof area that is the upper bound. There are other factors involved. Next slide. So moving on from the technical potential, one typically then tries to estimate what would be the retail bill savings for a consumer of a certain rate class or in a certain year. And these are usually ultimately expressed in the payback period of the system. So this was a study that our colleague did that looked at how rate design affects the economics of solar. And I think this has been a topic of a lot of debate over the last 2 years of, okay, so many states have introduced net metering, but what is the successor to net metering? How do we reform retail rates to better align the price signals between the bulk power and the distribution side of the grid? So there are many aspects to the rate structure. It's really not the average rate that matters, it's the marginal value. How much savings does the consumer see by reducing their consumption by 1 kilowatt hour? Because the average rate is not the marginal rate. There could be a fixed charge, there could be a demand charge. Both of those would indicate that the average cost of electricity is higher than the marginal value of reduced consumption. And likewise, there could be policies in the opposite direction, things like time use rates or tiered rates that provide a higher marginal value than the average value. So this study looked at what is the relative importance. So many of the aspects that seem to be quite important are fixed charges, minimum charges, and also moving away from purely volumetric charges to those that incorporate more time use components or more demand-based components. Next slide, please. So at this point, we've estimated the technical potential of solar in the territory, and we've also estimated its economics or payback period. And the next step is to relate the payback period to the ultimate market share or carrying capacity of the system. So many utilities tend to use similar assumptions about the elasticity of demand or the willingness to pay for solar. So here you can see the range of willingness to pay curves, or also called willingness to adopt. And so you can see that there is quite a bit of range. So if we just take a 5-year payback, some utilities project as little as 10% market share for a 5-year payback, and some as high as 40%. And these do tend to vary by sector. We tend to see higher willingness to adopt in the residential sector than in the commercial one, as well as different willingness to pay for new construction versus retrofit opportunities. So I think that it's also important to recognize that payback period is simply one metric that one can use to relate what fraction consumers might adopt. But there are many others, such as amount of retail bill savings or the percentage of the bill that's reduced, and so forth. And there's also a wide range of sophistication of the modeling to how well the willingness to adopt curves are actually calibrated versus just elicited preferences. Next slide, please. So finally, we have the diffusion phase of the modeling, and this is relating the maximum market share to how much is actually adopted in each year. This is a very old model. The Bass diffusion model was invented in the 60s to forecast market share of consumer technologies. And it posits that adoption of new technologies occurs sequentially, but first by innovators and then early adopters. But the other aspect is that it follows the sigmoid or S-shape pattern of adoption. That early adoption tends to look linear, tends to look relatively modest, but at some point the adoption rate continues to accelerate. There's a tipping point. And so I think the thing to take away is just because adoption seems low now, by no means suggests that it will continue to increase in a linear trend. It could transition from what looks like a linear trend to an exponential trend. Next slide, please. So this study looked at what is the historic adoption of other consumer technologies, everything from radios to dishwashers to colored televisions. And so the few things that we can take away from this is that there is a strong precedent for using S-curves in the diffusion of other technologies. Now, these are not necessarily all perfect benchmarks for distributed solar. I think, as I mentioned earlier, distributed solar is often thought of as a way to save on your electricity bill. It has a monetary economic component, whereas you really can't say what is my payback period for a radio or television. It improves my lifestyle insofar as anything else. But the other things we can take away is there's a highly variable time to saturation, but most technologies are measured not in years but in decades to reach full saturation. And then I think the other thing to take away is that the parameter fit, or the time to saturation, say the number of years between 5% market share to 95, is very sensitive to the observed data. As you see, no technology on this chart has perfectly followed in this shape. You can see clear dips for the Great Recession, for World War II, for many other exogenous factors that affect uptake over time. So while we do recommend that regressions are used to estimate the vast diffusion model, but it's also important to understand that it is sensitive to observed data, particularly when there isn't a lot of historic data to use to calibrate the model. Next slide. So after we have forecasted the total amount via the S-curve, the next step is to try to disaggregate it, to either the feeder or the household level. There are some models that do project adoption natively at the household level, but many others don't. And so there's essentially three methods that one can use. One is we can just sort of agnostically say that distributed solar will be adopted strictly proportional to load. That's not a terrible assumption in absence of other data. We could also say it might be disaggregated proportional to the amount of existing adoption, that we know areas that are already adopting solar, and so future adoption will occur proportional to those existing areas. But I think the best approach is using some type of propensity modeling. So it combines both how load and population patterns matter, where solar is being adopted currently and where it might be adopted in the future, but also, and most importantly, using actual customer characteristics to suggest which types of customers are most likely to adopt. A propensity score is ultimately some measure of the probability of adoption. So I think the area, next slide please, that has used this the most is California. So this is PG&E's, Pacific Gas and Electric's, distribution resource plan for 2015. And so you can see that they've taken the total aggregate amount of adoption and just disaggregated it down to the feeder level. And that allows really improved insights into what parts of the distribution system might experience, might require hosting capacity upgrades. Next slide, please. So models differ in what factors they use to come up with a propensity score. Some of them are purely theory-driven. Others are data-driven models where sort of throw all the variables in and see which ones best explain historic adoption. For PG&Es, they use different factors to explain residential and non-residential adoption, things like home ownership, amount of electricity used, income, and so forth. And on the non-residential side, building types, end uses, and so on. So ultimately, the planner has to come up with a propensity score and how factors affect either increasing or decreasing the probability of adoption, and then using this to allocate the system forecast down to either to individual consumers or to feeders as a whole. Next slide. So next, we talk about a few sort of cutting-edge advances in customer adoption modeling. So one method that one can take that goes beyond what we've just described is an agent-based model. So an agent-based model is very much a bottoms-up model that represents the interaction of different agents or ratepayers within the system. Its real advantage is allowing the planner to represent individual consumers, or they could be statistically represented consumers as well. But ultimately, understanding that the average household is not sufficient to understand the heterogeneity of consumers. Just because you live in a single-family home does not mean that the occupants of the home are identical. So it allows better representation of the diversity of customers and also a better representation of how consumers actually make decisions. But there are other methods altogether. So discrete choice models are another popular method of simulating the customer adoption process. Discrete choice models are very well established and they're used for soliciting customer preferences for different bundles of goods. how much, say, someone might trade off backup power versus the cost of that backup power versus retail bill savings. So it's a method that is data-driven and can be used to understand combinations of choices. And then I think the third advance, which is really just starting to emerge now, is modeling co-adoption of other technologies. The most common one right now is distributed solar and storage adoption. But of course, we can also think about the simultaneous adoption of solar and energy efficiency, demand response, storage, electric vehicles, and so on. We can go down the alphabet of all the DER technologies. Next slide, please. So now kind of coming back full circle to load planning, or sorry, load forecasting. So if we've followed everything to date that I've described, we've come up with a total adoption forecast, but we still need to implement it within the load forecast. And so one approach to really bear in mind here is that we do need to account for the interaction of DER adoption with load forecast. When it comes to empirical loads, we really are ultimately measuring the net load, the net amount of consumption from the end user to the bulk power system. But in fact, their gross load, or their actual load, meaning the consumption pattern without distributed energy resources, may be very different than the net load profile. So here you can see one of the methods that PJM used. So what they observe is the blue line. The blue line is, for example, that diurnal pattern of load. But the red line is the actual amount of load had DPV not existed. So what they have to do is develop a backcast forecast of the generation of distributed solar, and then add that back in to the historically observed net load, and that allows them to forecast the actual load, or the gross load. So this probably is not too important for territories that have small amounts of distributed solar. If your penetration rate is less than 1%, then it probably isn't too big of an issue. But of course, there could be, just because the penetration is 1% territory-wide, it could be much higher in certain areas of the distribution system. Okay, next slide. So here we provide other examples of interactions of distributed energy resources in transmission planning. I'm not going to go into each of them in great depth. You can refer to each of these studies at your own leisure. But some of the high-level things is we may consider distributed solar not just in the distribution resource plan, but also as an overall resource option, for example, in the integrated resource planning. So CAISO currently their planning process works by first identifying transmission needs that are needed to meet the reliability criteria, but then examining whether distributed solar can actually contribute to that reliability criteria, and then if so, is it cost effective to encourage its adoption as a resource option of meeting the future resource need. And there's many others here. So improving methods for locating distributed solar within the system, how one can disallocate adoption forecasts in absence of the observations of where the adoption is occurring, and so forth. Next slide, please. So I think that I mentioned this a little earlier, that most of the methodology has been focused on distributed solar. That is probably the largest distributed generation resource on the grid today, maybe apart from CHP. But there are many other resources that should be forecasted. So some DERs are similar to DPV in the sense that they can be installed behind the meter or in front of the meter. They can be adopted by multiple types of ratepayers, and that their basic value proposition is that they can reduce consumption, therefore increase bill savings. I think that there are many other emerging technologies where we don't have enough historic data to calibrate models, and so we may need to look to other benchmark technologies where if we can't estimate a model with the data on hand, then we need to benchmark either a different region or a different technology altogether. And then other DER technologies are really totally different than distributed solar. So the main one that comes to mind is CHP, where it is very specific to its end use. It tends to be installed by large end users, primarily industrial users, in which case a sort of broad-brushed approach may not be appropriate, and in fact, local knowledge from distribution planners may be more valuable than a top-down model. Next slide, please. So this is where I get to talk a little bit about the work that I do. So as I mentioned at the top of the hour, so one of the main focuses in my research is on developing these methodologies and developing the tools that people can use on their own to come up with adoption forecasts. So we're currently funded, NREL and my team, to open source our model called DGen. It's a distributed energy resource customer adoption model. We're working with planning staff in all 7 of the ISO RTOs to jointly develop adoption forecasts and build capacity in the ISOs to use the tool to develop their own forecasts going forward. We are right on the cusp of releasing our alpha version of the tool that will be released next month. And then the full version will be released to the public later this September. So if you are really itching to do these forecasts yourself, which we're encouraging, and we'd love to work with you, please visit our website, please sign up for our mailing list. And we are looking for additional partners because from our perspective, we want to see the tool used in practice. We don't want to, be instructive. We don't want to be prescriptive on how to use it. We want people to use it to come up with their own forecasts in the way they best see fit. So this figure shows projections of deployment rate for all of the 7 ISOs. And there's a wide range of future forecasts 20 years from now, anywhere from 1% penetration to nearly 8% penetration in CAISO. Next slide, please. So our project really has 4 objectives. As I mentioned, the primary objective is to open source this model so that utilities, public utility commissions, state energy offices, and so on can develop customized adoption forecast scenarios for themselves, that they have the tools they need to run their own scenarios. If you don't want to run the model yourself, then we are also developing scenario-based forecasted DR adoption for ISOs, for states, and all the way down to each county. So that data will be available soon. You can download the data yourself, or you can use our interactive web application. So I think the purpose of that is, if you don't have the time or expertise to develop your own forecast, you can use off-the-shelf data as a quick start. We also think that it's important to advance the state of the art and try to standardize methodology. So the example I always use is there are pretty well-established methods for doing capacity expansion modeling, for doing security constrained unit commitment. We have a pretty good consensus on what methods are most appropriate for those. But as you can see, there's still quite a range of methods that are used to forecast DERs. So we want to try to standardize those and communicate what are the best practices so people can compare models more easily. And then finally, we want to improve capabilities at ISOs and their constituents to incorporate DER forecasts into their market modeling and other long-term planning studies. Next slide, please. So finally, I would try to think about, if I was a regulator, what kind of questions might I ask at a docket or commission meeting for the quality of the forecast that's presented to me. So these are some of the things that you might ask about the planner that's presenting a forecast to you. So number one, what are the factors that went into the forecast of adoption? How are customer economics included, and how does that change? How are the forecasted customer economics changing over time within the forecast? Does the forecast account for the tendency of technologies to follow an S-shaped curve? As we showed previously, over 10, 15 consumer technologies have followed an S-shaped curve, not always perfectly, not as a perfect S-curve, but there does tend to be an S-shaped curve over time. Have you compared your forecast to other forecasts, for example, from third parties, from national labs, from consultants and so forth? So it is always good to get a variety of opinions, and ultimately we don't have to include every opinion, but it is good to see the range of potential opinions. And then finally, account for uncertainty in the forecast? So, as I said, it's impossible to perfectly forecast how consumers make decisions. We're not modeling electrons flowing on the distribution line here. We're trying to model how people make decisions, how behavior impacts adoption, and so we need to be humble about the role of uncertainty in the future forecast. Okay, thank you so much for your time, and I'd be happy to take any questions at this point.
That was great, Ben. Thank you. I have a couple of questions. Carrie, do you want to tee these up?
Oh, sure. It's up to you, Lisa.
Okay. Well, I'll just go for it here because I think the first one is sort of like a question that I have. 10 years ago, 15 years ago, I used to hear from utilities as a regulator that they can't predict what individual customers will do with respect to deploying distributed resources like solar, combined heat and power, which could be quite a bit larger. And so they need to build power plants to meet loads as if there won't be any additional adoption of distributed resources. So that's like 10, 15 years ago. How have utilities and regional transmission operators' views changed?
Thank you. That's a great question. I think we haven't perfectly solved that problem, of course, but I think there is a growing recognition that, if you recall my slide earlier on the cost of misforecasting, there's a growing recognition that DERs are here. We don't know exactly how much will be adopted, but it's somewhere between 0 and 100% penetration. I think we can all agree it's somewhere around there. So we should incorporate DERs into our load forecasting, into our distribution system planning. We can't perfectly understand how consumers will make adoption decisions, but similarly, we can't perfectly understand the price of natural gas 10 years from now. We can't perfectly understand what new technologies might emerge. So I do believe that forecasting is a useful tool. It's a useful tool for understanding the range of potential outcomes, but we still should be humble about the amount of uncertainty and understanding what are the range of potential outcomes for example, for our low adoption forecast all the way up to the high adoption forecast. That at least allows us to bound the problem and from there have a little more clarity in the decision making.
That's great. Thanks. Debbie Liu is going to talk tomorrow a bit more about multiple scenarios, and I think that's an important strategy for answering the question. I have one more question before we get to our last but not least presentation of the day on demand flexibility. If a utility doesn't have high penetration of, say, distributed solar today, what, if anything, might a public utility commission want to see from that utility with respect to load forecasting, say over the next 5 or 10 years, whether it's in an integrated resource planning context or distribution planning? They just don't have much today, but what should they be, doing about that in the next 5 or 10, to show for a plan that might have a planning horizon of 5 or 10 years from now?
Sure, thanks. Well, I think that fits very well with the talk I just gave. So, the adoption of distributed solar, for example, has tended to follow the price of retail electricity. So it's first really taken off in Hawaii and California, which has some of the highest costs of retail electricity. It's been much lower in other states or other utilities that have lower costs of retail electricity. But we continually see declines in the cost of distributed and utility scale solar. So just because it's not economic today, and just because it's not being adopted today, does not mean that it will continuously, for the perpetual future, not be adopted, going forward 10 years from now. So what I would like to see, if I were in that circumstance, would be first a calculation of what are the economics of solar today in our territory, and what might they be 10 years from now if we assume continued improvements, whatever is a reasonable amount of continued improvements in the solar technology costs. Because again, just because they're not competitive today does not mean that there will come a point in time if costs continue to decline where they'll be cost competitive in every territory. So I would like to see a forecast that at least acknowledges that even if we haven't seen adoption today, what conditions would need to be true and when those conditions might be met in the future.
Thanks, Ben. That was a really helpful and insightful response.